Out there, beyond the familiar glow of stars and the familiar darkness we call night, lies a realm so vast and so strange it defies everything we think we know. Picture this: a sea of invisible particles, swirling energies, and forces so powerful they could tear apart worlds in an instant. This is the intergalactic medium, the hidden fabric of the cosmos, and it holds secrets that challenge even the brightest minds in science. Think of it as the universe's greatest unsolved puzzle, a place where the laws of physics bend, where light itself can vanish, and where mysteries lurk in every direction. And today, we're diving deep into 30 of the most mind-bending enigmas hidden within this cosmic frontier. What makes the intergalactic medium so fascinating isn't just its scale, though it stretches across billions of light years, but the sheer unpredictability of what exists within it. Imagine gases so thin they're barely there, yet somehow they shape entire galaxies, or magnetic fields stronger than anything we've ever measured, twisting space itself into knots. Somewhere in that darkness, there could be answers to questions we haven't even thought to ask yet. What if I told you some of these mysteries might rewrite our understanding of reality? That somewhere in the void between galaxies, there might be clues to the origins of everything, even the birth of the universe itself. This isn't just a journey through space, it's a journey through the unknown. And the best part, you don't need a telescope or a degree in astrophysics to come along. All you need is curiosity, because over the next 30 revelations, we'll uncover truths about the cosmos that are as thrilling as they are baffling. From ghostly particles that pass through you right now without a trace, to the whispers of ancient explosions echoing across the void, each mystery pulls us deeper into the grand adventure of discovery. So buckle up, we're about to explore the most incredible, the most puzzling, and the most awe-inspiring secrets the universe has kept hidden until now. The first mystery that shatters our understanding of the cosmos is something called the Missing Baryon Problem. Here's the thing: when scientists calculate how much normal matter should exist in the universe based on the Big Bang's afterglow, the numbers just don't add up. Nearly half of the baryonic matter, the stuff that makes up stars, planets, and even us, seems to have vanished without a trace. But how does something as fundamental as matter just disappear? The answer might lie in the vast, almost invisible web of gas and plasma stretching between galaxies. Picture the universe as a colossal spider's silk, with strands so faint they're nearly impossible to see. This is the warm, hot intergalactic medium, or WIM, a diffuse sea of superheated particles hiding in plain sight. Detecting it is like trying to spot a single candle flickering in a foggy field at midnight. X-ray telescopes and ultraviolet observations give us glimpses, but the signals are so weak they often slip through our instruments. Some theories suggest this missing matter isn't lost at all, it's just hiding in these thin, scorching filaments, too spread out to shine like stars but still shaping the universe in ways we're only beginning to grasp. Others propose wilder ideas, like matter being locked away in exotic, undiscovered particles or even leaking into other dimensions. Whatever the truth, solving this puzzle could rewrite the cosmic ledger, forcing us to rethink where and what matter really is. And that's just the first mystery. The deeper we look, the more questions we uncover. The cosmic web is the universe's grandest architecture, an invisible scaffolding of gas and dark matter that stretches across the void like the veins of a colossal, living organism. These filaments, some spanning hundreds of millions of light years, act as highways for matter, funneling gas into galaxies and stitching the cosmos together in a delicate balance of gravity and motion. Yet for something so fundamental, it's astonishing how little we actually see. Most of this structure is so faint, so diffuse, that it slips through our telescopes like smoke through fingers. Scientists have pieced together its existence not by direct observation, but by studying the shadows it casts, When light from distant quasars, the brilliant cores of active galaxies, passes through these filaments, specific wavelengths get absorbed, leaving behind a fingerprint in the form of absorption lines. It's like holding a flashlight behind a fine mesh screen. You might not see the threads, but the pattern of light and shadow reveals their presence. These quasar absorption lines are cosmic breadcrumbs, guiding us toward understanding the web's hidden geometry. But the real challenge lies in mapping something so vast and elusive. Cutting-edge simulations run on some of the world's most powerful supercomputers recreate the universe's evolution from the Big Bang to today, tracing how gravity sculpted this intricate network over billions of years. The simulations match the sparse observational data we have, but gaps remain. Some filaments are too tenuous, their temperatures too extreme, or their densities too low for current instruments to detect. Others might be tangled in ways we haven't even predicted, twisted by forces we're only beginning to comprehend. What's truly mind-bending is how this web shapes everything we see. Galaxies don't form randomly, they cluster along these filaments like pearls on a string, fed by rivers of gas flowing along the cosmic currents. Without this hidden framework, the universe as we know it wouldn't exist. Yet for all its importance, we're still guessing at its full complexity. Are there entire sections of the web we're missing? Could unknown physics be altering its structure in ways our models can't yet account for? Every new observation peels back another layer, revealing just how much we have left to learn about the universe's hidden skeleton. Dark matter is the silent architect of the cosmos, an invisible hand shaping galaxies, bending light, and weaving the intergalactic medium into existence. Yet despite its overwhelming presence, accounting for roughly 85% of the universe's mass, it refuses to reveal itself. No light, no radiation, no direct signal. It's as if the universe is holding a conversation where we can only hear one side. The gravitational fingerprints are everywhere, stars orbiting galaxies too fast, light warping around cosmic voids, but the substance itself remains a ghost. So how does something we can't see dictate the structure of everything we can? Picture the intergalactic medium as a vast, turbulent ocean. Dark matter is the current beneath the surface, unseen but powerful enough to pull gas and dust into colossal filaments sculpting the cosmic web. Without it, galaxies would fly apart, and the delicate balance holding the universe together would unravel. Yet for all its influence, dark matter particles slip through our detectors like shadows through a net. Scientists have two leading suspects for what dark matter might be. The first are WIMP, weakly interacting massive particles. These hypothetical heavyweights barely interact with normal matter, making them nearly impossible to catch. Underground labs like Italy's Gran Sasso facility run experiments in pitch-black caverns, shielded from cosmic noise, waiting for the faintest shudder of a WIMP collision. After decades, the detectors remain eerily quiet. The second candidate, actions, are the opposite ultra-lightweight particles, so wispy they behave more like waves than matter. Think of them as cosmic whispers vibrating through magnetic fields. Experiments like the action dark matter tune in like a radio, hoping to catch their faint signal. But here's the twist: what if dark matter isn't one thing but many? Some theories suggest an entire hidden sector of particles, each with strange properties beyond our current physics. Others propose modifications to gravity itself, challenging Einstein's framework. The intergalactic medium complicates the puzzle further. Its diffuse gases might hold clues like traces of dark matter annihilation or decay, but teasing those signals from the noise is like listening for a single note in a symphony. Every failed detection narrows the possibilities, forcing scientists to rethink, adapt, and dig deeper. The answer could lie in the next generation of telescopes, particle colliders, or even a stroke of luck. One thing's certain: solving this mystery wouldn't just fill a gap in our equations, it would rewrite the story of the universe. And somewhere in the darkness between galaxies, the truth is waiting. Among the most baffling spectacles drifting through the intergalactic medium are the Lyman-alpha blobs, enormous, glowing clouds of hydrogen gas so vast they could swallow entire galaxies. These cosmic behemoths stretch across hundreds of thousands of light-years, radiating a ghostly ultraviolet hue known as Lyman-alpha light. Hubble's breathtaking images reveal them as ethereal halos, floating in the darkness like celestial jellyfish, their edges shimmering with energy we can't fully explain. What powers these radiant giants? One leading theory points to frenzied star formation. Imagine a nursery where stars are born at a rate hundreds of times faster than in our own Milky Way, each new sun unleashing torrents of radiation that set the surrounding gas ablaze. In this scenario, the blobs are like cosmic fireworks. Their glow the combined light of countless stellar births. Yet when astronomers peer inside, many blobs show fewer stars than expected, leaving the intensity of their glow a puzzle. Another possibility ties them to the violent appetites of supermassive black holes. As these monsters devour matter, they belch out jets of energy that could heat surrounding gas to extreme temperatures, causing it to fluoresce. It's like holding a blowtorch to a cloud. Suddenly, what was invisible becomes a beacon. Some blobs even sit at the hearts of ancient galaxy clusters, where black holes are known to rage, fueling the suspicion they're cosmic signposts of destruction. Then there's the wild card. Could these blobs be evidence of something entirely unexpected? A few exhibit structures too orderly for chaos, with filaments and shells that hint at unknown physical processes. Some researchers speculate about exotic phenomena, perhaps collisions between dark matter particles releasing energy, or vast magnetic fields channeling gas into glowing patterns. The truth might lie beyond our current astrophysical playbook. What makes these blobs especially tantalizing is how they bridge scales. They're not just isolated oddities, they're intergalactic weather systems influencing how galaxies grow and interact. Their light, traveling billions of years to reach us, carries encoded clues about the early universe's chemistry and density. Each new observation peels back another layer, revealing how much we still don't understand about the forces shaping the cosmos. And as telescopes grow sharper, these glowing enigmas might finally give up their secrets or plunge us deeper into mystery. Deep in the cosmic voids, where galaxies are few and far between, astronomers have stumbled upon something that shouldn't be there: pockets of space overflowing with oxygen. This isn't just a slight imbalance. Some regions contain 10 times more oxygen than our best models predict. It's as if the universe left the gas stove on in rooms nobody uses, and no one can explain why. Oxygen, after all, isn't some stray element drifting aimlessly. It's forged in the hearts of massive stars and scattered across space in violent supernova explosions. So how did so much of it end up in the loneliest corners of the cosmos? One explanation points to the death throes of stars. When a supernova detonates, it flings heavy elements like oxygen into space at nearly a tenth the speed of light. Over millennia, these ejecta can travel far beyond their home galaxies, seeding the intergalactic medium with unexpected riches. But there's a problem: the math doesn't quite add up. Even accounting for countless stellar explosions, the sheer volume of oxygen in these remote regions suggests something more extreme. Could entire generations of stars have lived and died in now vanished dwarf galaxies, leaving behind ghostly oxygen clouds as their only trace? Then there's the galactic wind theory. Picture a spiral galaxy like our Milky Way, its core alive with star formation. The energy from those newborn stars drives powerful winds, capable of blasting gas clear out of the galaxy's grip. These winds might carry oxygen-rich material into the void, where it accumulates like cosmic driftwood. Observations of nearby galaxies, such as those in the Virgo cluster, show streams of gas stretching far into intergalactic space, tentative evidence for this process. Yet some of the oxygen excesses are so far from any visible galaxy that even this explanation strains credulity. Perhaps the most tantalizing possibility involves processes we haven't even discovered. Some theorists speculate about exotic phenomena like dark matter interactions generating oxygen as a byproduct, or primordial gas clouds from the early universe that were already enriched by unknown mechanisms. Others wonder if we're seeing the aftermath of colossal, ancient collisions, where entire galaxies merged and jettisoned their oxygen into the abyss. The truth might lie hidden in the faint spectral lines of distant quasars, their light altered by passing through these mysterious oxygen reservoirs. What makes this puzzle so critical is what oxygen reveals about the universe's chemical evolution. It's a cosmic ledger recording how elements have spread and transformed over billions of years. If our understanding of its distribution is flawed, it could mean rewriting chapters of astrophysics, from how galaxies form stars to how life-building ingredients are scattered across the cosmos. Every new telescope, from the James Webb to upcoming X-ray observatories, brings us closer to an answer. But for now, these oxygen-rich voids remain a stark reminder. Even in the emptiest places, the universe is full of surprises. Some of the universe's most baffling structures aren't colossal or brilliant, they're nearly invisible. Ultra-diffuse galaxies drift through the intergalactic medium like cosmic phantoms, their stars so thinly scattered that they barely cast a shadow against the blackness of space. These ghostly islands defy everything we thought we knew about how galaxies form. Take Dragonfly 44, for example, a galaxy roughly the size of the Milky Way, but with stars so sparse you could fly through it for light years and never spot one. Yet despite their faintness, these galaxies pack a shocking secret. They're teeming with dark matter. The puzzle begins with their birth. Conventional galaxies form where gas pools under gravity's pull, condensing into stars that light up the darkness. But ultra-diffuse galaxies seem to have missed the memo. Some may be failed galaxies, places where gas was too sparse or too violently stripped away to ignite robust star formation. Others might be the battered survivors of cosmic collisions, their outer stars torn loose by gravitational tides, leaving behind a dark matter-rich core. Then there's the environmental factor. Many of these wispy giants lurk near galaxy clusters, where the gravitational tug of war and scorching intergalactic gas could have starved them of star-forming fuel over billions of years. But here's where the plot twists. Not all ultra-diffuse galaxies fit this mold. Some float in isolated voids far from any disruptive neighbors. Others, like the oddly pristine NGC 1052DF2, appear to have almost no dark matter at all, a direct challenge to theories that rely on it as their gravitational anchor. This split suggests multiple origins, as if the universe is crafting these ghostly galaxies through entirely different recipes. One might be a galactic skeleton. It stars the last remnants of a violent past, while another could be a quiet relic, frozen in time since the cosmos was young. The implications ripple far beyond these faint smudges of light. If dark matter can sculpt galaxies this diffuse, it forces us to reconsider how it interacts with normal matter, or if it interacts at all in ways we've yet to detect. Some simulations hint that ultra-diffuse galaxies could be the dark matter equivalent of cosmic fossils, preserving conditions from the early universe in their delicate structures. Others propose even wilder ideas, like invisible dark matter halos so expansive they gently cradle stars without squeezing them into brighter, denser formations. Every new discovery deepens the mystery. Advanced telescopes like the James Webb are now probing these galaxies' chemical compositions, searching for clues in the faint glow of their ancient stars. What they find might rewrite the rules of galactic evolution, revealing how environment, time, and unseen forces conspire to shape the universe's most elusive inhabitants. And as we peer deeper into the shadows, one thing becomes clear: the darkest corners of space still hold the brightest surprises. The universe sends us messages in bursts of radio energy so intense they outshine entire galaxies, yet last no longer than the blink of an eye. Fast radio bursts, or FRB, are among the most electrifying puzzles in modern astronomy. These flashes, some unleashing as much energy in milliseconds as the sun does in weeks, arrive from deep space without warning. But here's the twist. They might be the ultimate cosmic cartographers, revealing secrets about the intergalactic medium we can't see any other way. Every FRB carries a hidden fingerprint in the form of dispersion, a delay in its signal's arrival time caused by electrons in the space between galaxies. The longer the delay, the more material the burst has traveled through. It's like listening to an echo in a canyon. The way the sound stretches tells you how far it's traveled and what it's passed through. By measuring this dispersion, astronomers can map the invisible gas woven between galaxies, tracing structures too faint for telescopes to spot directly. Some FRBs even hint at bizarre, magnetized filaments or pockets of ionized gas where our models predicted emptiness. But what's creating these bursts? Some likely come from magnetized neutron stars with magnetic fields so strong they could strip the atoms from your body at 1,000 kilometers away. When these cosmic powerhouses undergo starquakes or magnetic eruptions, they might unleash FRBs like celestial lightning. Then there's the repeater phenomenon. Most FRBs are one-offs, but a handful, like FRB 121811, fire off repeatedly, sometimes in predictable patterns. These could point to orbital dynamics, perhaps a magnetar locked in a deadly dance with a black hole, or a neutron star plowing through a dense nebula. Of course, the wildest theories linger at the edges. Could some FRBs be artificial? The idea of alien megastructures, cosmic lighthouses, or power beams isn't entirely dismissed. Even if improbable, the notion forces us to question our assumptions. After all, nature often outdoes our imagination. What's undeniable is how FRBs illuminate the dark. Each burst is a probe lighting up the intergalactic medium like a flare in a cavern, exposing the distribution of matter, the strength of magnetic fields, and even the universe's expansion rate. With new telescopes like CHIME detecting dozens per month, we're on the brink of a revolution, one where these fleeting signals might decode the cosmos's hidden architecture. The universe should be darker, at least that's what every textbook and simulation tells us. Yet when astronomers peer into the depths of the intergalactic medium, they're bombarded by an inexplicable flood of ultraviolet light, far more than stars, galaxies, or even quasars should produce. It's as if someone left the cosmic lights on in a room with no visible bulbs. This too much light anomaly has sent researchers scrambling, forcing them to confront a glaring gap in our understanding of how energy moves through the cosmos. One of the most startling revelations came from the Hubble Space Telescope's observations of distant galaxy clusters. Even after accounting for every known light source, active galactic nuclei, young stars, supernova remnants, up to half the ultraviolet radiation remained unaccounted for. The signal wasn't faint or localized. It saturated vast regions of space, a diffuse glow with no obvious origin. Some scientists initially dismissed it as scattered starlight, but the intensity and uniformity defied that explanation. The light was too widespread, too consistent, almost as if it were baked into the fabric of space itself. Enter the dark stars hypothesis, a radical proposal that the universe might be littered with invisible primordial behemoths. These wouldn't be stars as we know them, but hypothetical objects forged in the extreme conditions of the early cosmos, powered not by nuclear fusion but by the annihilation of dark matter particles. Picture a sphere of hydrogen and helium, dense enough to trap dark matter at its core, where collisions would release energy as ultraviolet light. Dark stars could theoretically grow hundreds of times larger than our Sun, glowing faintly for billions of years without ever igniting fusion. If they exist, their collective light might solve the anomaly, but here's the catch: no one's ever seen one. Alternative explanations stretch the imagination further. Could decaying particles from the Big Bang, relics of a hotter, denser universe, still be shedding energy as UV light? Or might there be an entire population of tiny, faint galaxies, too dim for our telescopes to spot individually, but collectively bright enough to drown the cosmos in extra photons? Some theorists have even floated the idea of cosmic strings, defects in space-time left over from the universe's birth vibrating like guitar strings and emitting radiation as they shake. What makes this mystery so critical is what it reveals about our blind spots. The intergalactic medium isn't just empty space, it's a dynamic ecosystem with energy flowing in ways we're only beginning to map. If dark stars are real, they'd rewrite the story of how the first structures formed after the Big Bang. If it's something else entirely, we might need new physics to explain it. Every unanswered question about this ultraviolet excess is a reminder. The universe doesn't just hide its secrets in darkness sometimes, they're right in front of us, shining too brightly to ignore. Imagine stumbling upon a snowball floating in the middle of a volcano. That's the kind of paradox astronomers face when studying the universe's coldest gas clouds, clumps of frigid hydrogen drifting through the searing hellscape of the intergalactic medium. These cosmic ice cubes, some hovering just a few degrees above absolute zero, shouldn't exist, not here. The space between galaxies is a brutal environment, flooded with radiation and superheated plasma. Yet these clouds persist, untouched by the chaos around them, as if shielded by some invisible force. Could they be primordial relics, frozen fragments of the universe's birth that somehow survived 13 billion years against all odds? The coldest of these anomalies, like the ones in the Virgo cluster, defy every expectation. Gas that cold should have been vaporized eons ago by the million-degree plasma surrounding it. Instead, these clouds cling stubbornly to their chill, like ice cubes refusing to melt in boiling water. One theory suggests magnetic fields might be cocooning them, invisible barriers strong enough to repel the scorching intergalactic winds. Picture a soap bubble's delicate film, but woven from cosmic forces, shielding the fragile hydrogen inside from the furnace beyond. Then there's the dark matter connection. Some researchers speculate these clumps aren't just floating passively. They might be anchored by unseen halos of dark matter, their gravity creating a protective well that keeps the gas cold and dense. It's like a celestial refrigerator with dark matter acting as the insulation. But here's the catch: if that's true, these clouds could be the tip of an iceberg, literal evidence of dark matter's hidden architecture, mapping its distribution in ways our telescopes can't directly observe. Yet the most tantalizing possibility is that these cold clumps are fossils from the universe's first minutes. In the chaos after the Big Bang, pockets of hydrogen might have remained untouched by the intense radiation bathing the cosmos, their atoms never heated, never stirred. Finding one would be like discovering a perfectly preserved dinosaur bone, a snapshot of conditions before galaxies even formed. The challenge, confirming their age, requires studying isotopes nearly impossible to detect across such vast distances. What's clear is that these icy enigmas are more than cosmic curiosities. They're stress-testing our understanding of thermodynamics, magnetic fields, and the very nature of the intergalactic medium. Every new observation peels back another layer, revealing how much we still don't know about the delicate balance between heat and cold, chaos and order, in the vast expanse between the stars. And somewhere in that darkness, these ancient, frozen whispers dare us to unravel their secrets. The space between galaxies isn't just empty, it's threaded with invisible force fields strong enough to bend the paths of cosmic rays, yet so faint they evade direct detection. These are the intergalactic magnetic fields, and their existence challenges everything we thought we knew about the universe's structure. Picture a spider's web, but one spun from pure magnetism, stretching millions of light years across voids so vast they could swallow entire galaxy clusters. The odd part, we still don't know how these fields got there or why they persist in regions where almost nothing else exists. One camp of theorists argues these fields are primordial relics from the universe's violent birth. In the first fraction of a second after the Big Bang, quantum fluctuations might have imprinted magnetic seeds into spacetime itself. As the cosmos expanded, these seeds stretched into the faint, sprawling filaments we detect today. There's tantalizing evidence in the cosmic microwave background, subtle twists in ancient light that could be fingerprints of these early magnetic fields. If true, they'd be the oldest magnets in existence, older than stars or galaxies, a fossilized force from the dawn of time. But there's a rival theory: galactic pollution. Supernova and active black holes belch out jets of charged particles, which can carry magnetic fields into the void like invisible ink bleeding through water. Over billions of years, these outflows might have painted the cosmos with magnetism, turning the intergalactic medium into a patchwork quilt of borrowed fields. Observations of galaxy clusters support this. Some show magnetic fields aligned with ancient jets, as if the galaxies themselves are graffiti artists tagging the cosmos. The stakes go beyond mere curiosity. These fields shape how cosmic rays, ultra-fast particles from distant cataclysms, travel across the universe. Without magnetism to deflect them, these rays would streak through space in straight lines, making their sources easy to trace. Instead, they spiral and twist, turning intergalactic space into a maze. Some rays might even be trapped for eons, bouncing between magnetic field lines like pinballs, their origins erased by the journey. What's truly bizarre is how uniform some of these fields seem. In certain voids, the magnetism aligns over incomprehensible distances, as if the universe had a giant magnetic north. That's hard to square with the chaotic outbursts of galaxies or the randomness of primordial creation. Could there be something else at work, a process we haven't even imagined yet? The answer might lie in the next generation of radio telescopes, which could finally map these ghostly fields in detail. Until then, they remain one of the cosmos' quietest yet most profound mysteries. Tucked away in the cosmic tapestry are tiny, brilliant anomalies that glow with an eerie green light, so unusual astronomers dubbed them green pea galaxies. These compact powerhouses, no bigger than a tenth of the Milky Way, punch far above their weight, blazing with star formation rates hundreds of times more intense than our own galaxy. But what makes them truly extraordinary isn't just their color or their frantic energy. It's how they might hold the key to one of the universe's greatest turning points, the epoch of reionization, when the first starlight tore through the fog of primordial hydrogen and lit up the cosmos. Green peas were discovered almost by accident in 2009, when volunteers sifting through data from the Sloan Digital Sky Survey flagged them as oddities. Their vivid emerald hue comes from doubly ionized oxygen, a signature of scorching young stars bombarding surrounding gas with ultraviolet radiation. In most galaxies, this glow is diluted by older, cooler stars, but green peas are virtually pure stellar nurseries, their light dominated by the fury of newborn suns. It's like comparing a forest fire to a candle. These galaxies burn so fiercely they illuminate fundamental processes usually lost in the noise, and that's where the intergalactic medium enters the story. Green peas aren't just glowing, they're leaking. Their ferocious stellar winds and supernova eject gas at staggering speeds, blasting heavy elements like oxygen and nitrogen into the void. This isn't a gentle seepage, it's a fire hose of enriched material, spraying the surrounding space with the building blocks of future stars and planets. Some studies suggest these outflows might even pierce through their host galaxies' dark matter halos, delivering chemical wealth directly to the intergalactic medium. If so, green peas could be cosmic alchemists, transforming pristine gas into the enriched reservoirs that later galaxies will use. But their most tantalizing role ties them to the universe's adolescence. During reionization, roughly 1 billion years after the Big Bang, the first galaxies had to carve bubbles of ionized hydrogen in the surrounding fog, a process requiring staggering amounts of UV light. Green peas, with their blistering radiation, are perfect analogues for those pioneers, Observing them today is like finding a living fossil, a relic of the mechanisms that transformed the cosmos from darkness to light. Some researchers argue these tiny galaxies might have done the heavy lifting in reionization, their collective UV outpouring overwhelming the hydrogen haze where larger, galaxies couldn't. Yet puzzles remain. Why do green peas have such bizarre chemical cocktails? Some show nitrogen levels 6 times higher than expected, as if their stars formed from gas pre-seasoned by unknown processes. Others host supermassive black holes far too large for their size, suggesting violent histories we've yet to unravel. And then there's their distribution. Why are they so rare, vanishing from surveys beyond a certain cosmic distance? The answer might lie in their dependence on specific gas flows, or perhaps they're a fleeting phase, burning out as quickly as they ignite. What's certain is that these tiny emerald giants are more than cosmic oddities. They're laboratories for understanding how galaxies interact with the intergalactic medium, how the universe lit its first lights, and how the raw materials for life get scattered across the void. Every new observation peels back another layer, revealing how much we still don't know about the small players in the grand cosmic drama. The universe runs on a grand cycle of creation and destruction, stars forging heavy elements in their cores, then scattering them across space in violent supernova explosions. Over billions of years, these metals should have spread evenly, seasoning the cosmos like salt in a vast ocean. Yet when astronomers peer into certain corners of the intergalactic medium, they find voids where the expected heavy elements are curiously absent. It's as if someone erased entire chapters from the periodic table, leaving behind gaps that defy our models of cosmic chemistry. One clue lies in the timing. Heavy elements don't just appear, they're forged in stellar furnaces and hurled into space by supernova or stellar winds. But this process isn't instantaneous. Imagine tossing a handful of glitter into a lazy river. It takes time for the flakes to disperse, and some might clump or sink before reaching the far bank. Similarly, metals ejected from galaxies might take hundreds of millions of years to fully mix with the surrounding gas. In regions where star formation peaked late, or where supernova were unusually sparse, the intergalactic medium could still be playing catch-up. Then there's the hiding place theory. Heavy elements might not be missing at all, just camouflaged. In the scorching filaments of the warm, hot intergalactic medium, metals could exist in highly ionized states, their spectral signatures blurred beyond recognition by the extreme temperatures. It's like searching for a specific grain of sand in a desert. The tools we have might not be fine-tuned enough to spot them. X-ray observatories like Chandra have detected hints of this hidden wealth, but the signals are often too faint to confirm. But the most provocative idea challenges our assumptions about galactic winds, the forces that blast metals out of galaxies in the first place. Not all winds are created equal. In low-mass galaxies, stellar explosions might lack the energy to propel heavy elements fully into the void, leaving them trapped in extended halos. In denser regions like galaxy clusters, the surrounding intergalactic gas acts like a wall, preventing metals from escaping. This could create metal deserts, vast expanses where enrichment hasn't yet penetrated, preserved like cosmic time capsules. The implications ripple far beyond these empty pockets. If heavy elements are unevenly distributed, it could mean some regions of the universe are more hospitable to life than others. Planets need metals to form, and life as we know it requires elements like carbon and iron. A galaxy born in a metal-poor zone might struggle to build rocky worlds, let alone complex chemistry. Yet even in these apparent voids, surprises lurk. Recent studies of distant quasars suggest some empty regions might contain ultra-diffuse metal clouds, their signals drowned out by brighter foreground objects. Others hint at dark matter's role. Perhaps its gravity guides metal-rich gas into narrow streams, leaving surrounding areas barren. Every new observation adds another piece to the puzzle, revealing a universe more nuanced than we ever imagined. And somewhere in these silent, seemingly empty spaces, the missing elements might be waiting hidden in plain sight. Hidden in the vast stretches between galaxies, there might still be untouched relics, clouds of gas so pristine they carry the exact same chemical signature as the universe mere minutes after the Big Bang. These cosmic time capsules, composed almost entirely of hydrogen and helium, would be the closest thing we have to a direct sample of the infant cosmos. But finding them is like searching for a single unaltered snowflake in a blizzard of pollution. Over billions of years, stars and supernova have peppered the intergalactic medium with heavier elements from carbon to iron. So how could any pocket of gas remain uncontaminated? And if they do exist, what secrets could they whisper about the universe's first moments? The hunt hinges on quasar absorption spectra, one of astronomy's most powerful forensic tools. When light from a distant quasar passes through a gas cloud, certain wavelengths get absorbed, leaving dark lines in the spectrum like barcodes. Each element stamps its own unique pattern. Oxygen leaves one set of lines, carbon another. But pristine gas would show almost nothing but hydrogen and helium, with no fingerprints of heavier elements. The challenge, even the faintest trace of contamination, a few atoms of oxygen per million, can obscure that primordial purity. It's like trying to prove a glass of water has never had even a single grain of salt dissolved in it. Some tantalizing candidates have emerged. In 2011, astronomers studying quasar absorption lines spotted a gas cloud over 12 billion light-years away with metal levels at least 10,000 times lower than the Sun's. Then, in 2018, another team found a cloud so pristine its oxygen levels were below 1/10,000th of the expected value. These discoveries ignited debate. Are we seeing genuine relics or just regions where metals are unusually sparse? The problem is cosmic recycling gas doesn't stay in one place. Winds from galaxies, collisions between clusters, and even the gentle tug of dark matter can stir the intergalactic medium, mixing pristine and polluted gas over time. Alternative theories suggest these clouds might not be primordial at all, but rather reset by some unknown process. Imagine a cosmic filter, perhaps a vast magnetic field sieving metals out of a gas stream, leaving behind purified hydrogen. Or maybe these clouds are the remnants of ancient voids, regions so empty they avoided star formation entirely, preserving their original state by sheer isolation. The most radical idea, they could be the fallout of dark matter interactions where certain particle decays preferentially remove heavy elements, leaving behind a ghostly residue of pure hydrogen. What's at stake goes beyond curiosity. Pristine gas clouds are the control group of the universe, a baseline to test our theories of nucleosynthesis and cosmic evolution. If they match predictions from Big Bang models, it's a triumph for astrophysics. If they don't, it could mean revising our understanding of the early universe's chemistry. Even more thrilling is the possibility that some of these clouds might be cooler and denser than expected. Pockets where conditions are just right for the formation of the universe's very first stars. Population: 3 stars, hypothetical giants made purely of hydrogen and helium, whose existence we've yet to confirm. For now, the hunt continues. New instruments like the James Webb Space Telescope and next-generation spectrographs are scanning deeper and finer, searching for that elusive, unblemished signature. Every candidate cloud is a potential Rosetta Stone waiting to decode the universe's earliest chapters. And if we find one truly untouched, it won't just be a discovery, it'll be a window straight back to the dawn of everything. Hidden in the darkness between the stars are ghostly islands of gas galaxies so devoid of stars they barely cast a shadow. These are the dark galaxies, cosmic phantoms detected not by the light they emit, but by the faint whispers of their gas. Imagine an entire galaxy spanning thousands of light-years, where only a handful of stars flicker against an ocean of near-total blackness. They challenge one of astronomy's most basic assumptions, that galaxies are defined by their stars. Yet these enigmatic structures exist, and they might hold the key to understanding why some corners of the universe remained forever dark. The discovery of dark galaxies rewrote the rules. Traditional telescopes designed to capture starlight almost missed them entirely. It was only when astronomers turned to radio waves tuning into the faint emissions of hydrogen gas that these shadows emerged from the void. One of the first detected, a sprawling structure named Virgohi 21, contained enough gas to birth billions of stars, yet it had almost none. The question wasn't just how this happened, but why. What cosmic quirk left these reservoirs of potential untouched, like unlit kindling in a universe ablaze with stellar fires? Dark matter provides the first clue. These galaxies are drowning in it, their mass dominated by unseen halos so dense they should have triggered star formation eons ago. In normal galaxies, dark matter's gravity pulls gas into dense clouds where it cools, collapses, and ignites into stars. But in dark galaxies, something went wrong. Perhaps the gas was too hot, kept turbulent by nearby galaxy collisions or relentless cosmic radiation. Maybe magnetic fields threading through the gas like invisible scaffolding prevented it from clumping. Or the dark matter itself might be to blame, its distribution so smooth it couldn't spark the necessary density for stars to form. Then there's the isolation factor. Many dark galaxies drift in the emptiest reaches of the intergalactic medium, far from the gravitational jostling that typically stirs galaxies to life. Without the shock waves of passing neighbors or the crush of a galactic cluster, their gas might have simply lingered, untouched, unlit. Like a rain cloud that never falls, these reservoirs could be frozen in time, preserving conditions from an earlier, quieter universe. But the plot thickens. Some dark galaxies aren't entirely starless. A few, like the famous Dragonfly 44, host sparse collections of ancient stars, relics of a failed attempt at stellar birth. These stragglers hint at a more complex history. Perhaps these galaxies tried to form stars, only to have their gas stripped away by violent encounters or blasted into oblivion by supernova. Others might be the victims of cosmic starvation, their gas slowly siphoned off by larger neighbors over billions of years, leaving behind a skeletal framework of dark matter and fading starlight. What makes these phantoms so invaluable is what they reveal about failure. Most of astronomy focuses on success, the brilliant galaxies, the blazing stars. But dark galaxies are the universe's abandoned blueprints, showing us what happens when the recipe goes wrong. They force us to ask how many other galaxies almost were, how much of the cosmos remained potential rather than reality, and could some of these dark structures still awaken, given the right nudge from a passing wave of intergalactic gas or a collision with another phantom. For now, they linger in the shadows, their secrets locked in the faint radio murmurs of their gas. New telescopes, like the Square Kilometre Array, aim to uncover thousands more, mapping this hidden population in unprecedented detail. Each discovery peels back another layer, revealing how fragile the balance is between a galaxy that blazes with light and one that remains forever dark. When galaxies collide, they don't just rearrange stars. They send titanic shock waves rippling through the intergalactic medium like cosmic tsunamis. These are no ordinary waves. They stretch for millions of light years, traveling at speeds that defy comprehension, and they carry enough energy to reshape entire galactic neighborhoods. Picture the aftermath of two spiral galaxies smashing together, their gas clouds compressed, their magnetic fields twisted, and their dark matter halos sloshing like water in a shaken bowl. The resulting shock fronts carve through the surrounding void, leaving behind turbulence so extreme it can rewrite the rules of star formation. One of the most dramatic examples lies in the Bullet Cluster, where two galaxy clusters collided with such force they created a shock wave visible in X-rays. A cosmic pressure wave so powerful it heated the intergalactic gas to hundreds of millions of degrees. But here's the twist: these shocks don't just destroy, they also create. As the waves plow through the medium, they compress gas into dense, cold filaments, sparking bursts of star formation in their wake. It's like a celestial domino effect, chaos birthing new order. In some cases, these shock-triggered stars form in bizarre, isolated pockets far from any galaxy, as if the universe itself is scattering seeds in the void. Yet the real mystery lies in what we can't see. Shock waves don't just affect normal matter, they also leave imprints on dark matter. Gravitational lensing maps of colliding clusters reveal dark matter behaving strangely, displaced from the gas by the violence of the impact. Some theorists suggest these shocks might even excite dark matter particles, causing them to emit faint signals we've yet to detect. If true, intergalactic tsunamis could be our backdoor to uncovering dark matter's secrets, using the chaos of collisions as a natural laboratory. But the most unsettling possibility, these shocks might be far more common than we realize. Galactic collisions were rampant in the early universe, and even today, galaxy clusters merge in slow-motion crashes that last billions of years. Each event sends ripples cascading through the intergalactic medium, stirring the cosmic pot in ways we're only beginning to measure. Some of these waves could still be traveling, relics of ancient collisions whose echoes distort the gas around us, unseen and unmeasured. What's certain is that these tsunamis are more than just cosmic fireworks. They're architects of the universe, sculpting the distribution of gas, stars, and perhaps even dark matter itself. And as astronomers refine their simulations, probing how these shocks interact with magnetic fields and cosmic rays, one thing becomes clear: the space between galaxies is anything but calm. It's a seething, churning frontier where the echoes of ancient violence still shape the fate of everything we see. Deep in the intergalactic medium, astronomers have stumbled upon regions so thoroughly ionized they defy every model of cosmic evolution. These zones are drenched in ultraviolet and X-ray radiation, their atoms stripped bare of electrons far beyond what known energy sources should produce. It's like finding patches of desert so scorched they've turned to glass long after the wildfire passed through. The paradox cuts to the heart of our understanding. If quasars and young galaxies don't emit enough high-energy photons to explain this extreme ionization, what unseen force is at work? One leading suspect is a hidden population of faint, exotic objects. Picture thousands of rogue black holes, too small to power brilliant quasars but collectively bathing their surroundings in X-rays as they devour stray gas. Or perhaps collapsed stars we've yet to categorize, white dwarfs heated to unimaginable temperatures by dark matter annihilations in their cores. Some simulations even suggest decaying particles from the early universe, relics of a hotter epoch, might still be flooding these regions with ionizing radiation like slow-release cosmic batteries. But the plot twists when we examine these zones' locations. Many cluster near the relics of ancient galactic collisions, places where supermassive black holes may have once dueled, their gravitational waves rippling through the intergalactic medium long after the mergers ended. Could these waves have transferred enough energy to re-ionize the gas, like a pebble dropped in a pond that keeps radiating heat for eons? The timing matches. Some over-ionized regions appear precisely where models predict historic black hole mergers occurred billions of years ago. Then there's the wild card: our models might be fundamentally incomplete. Current reionization theories assume a uniform intergalactic medium, but what if dark matter's gravitational tugs have warped space into hidden chambers where radiation gets trapped and amplified? Or maybe magnetic fields, threading through the void like cosmic fiber optics, are funneling energy from distant sources into concentrated beams we can't directly trace. The implications ripple far beyond these odd zones. If we've underestimated ionization rates, entire chapters of cosmic history need rewriting. From how the first galaxies cleared their cosmic fog to why certain elements dominate the intergalactic medium today. Every unexplained photon represents energy unaccounted for, a puzzle piece that could reveal new physics or celestial phenomena hiding in plain sight. And as telescopes like the Chandra X-ray Observatory peered deeper, these over-ionized patches might finally give up their secrets or plunge us deeper into the unknown. The universe is full of ghost particles that pass through planets, stars, and even our bodies without leaving a trace. But what if the intergalactic medium hides an entire menagerie of phantoms we've yet to detect? Among the most tantalizing candidates are sterile neutrinos and actions hypothetical particles so elusive they make dark matter seem obvious by comparison. These could be the missing pieces to cosmic puzzles we don't even fully understand yet. Take sterile neutrinos first. Ordinary neutrinos are already cosmic escape artists, tiny, chargeless particles that barely interact with matter. Billions zip through you every second from the sun, and you'd never know. But sterile neutrinos would be even stranger. If they exist, they'd be heavier than their known cousins, oscillating in and out of detectable states like a quantum game of peek-a-boo. The intergalactic medium might be teeming with them, their collective mass subtly warping the growth of cosmic structures over billions of years. Some researchers blame them for oddities in the cosmic microwave background, those faint temperature fluctuations that shouldn't exist if our current particle physics models are complete. Then there are actions theoretical particles originally conjured up to solve a problem with quantum chromodynamics, but now hunted as potential dark matter constituents. Picture them as wispy, wave-like entities condensing in cosmic magnetic fields like dew on a spiderweb. Unlike bulky WIMP, actions wouldn't crash into detectors so much as vibrate through them, leaving only the faintest hum. Experiments like ADMCs are tuning into this frequency, using supercooled cavities to catch whispers of actions converting into photons. The intergalactic medium could be their concert hall, with magnetic filaments acting as cosmic strings strummed by particles we can't yet see. What makes these speculations so electrifying isn't just the particles themselves, it's how they might rewrite the rules. Sterile neutrinos could explain why some galaxies form too quickly in simulations, or why the universe's large-scale structure looks slightly clumpier than predicted. Actions might account for the universe's missing magnetism, or why certain cosmic voids seem unnervingly empty. Both could leave fingerprints in the way light from distant quasars dims as it passes through the intergalactic medium, subtle absorption lines that current telescopes strain to resolve. But the real shocker, these particles might not be alone. Some theories posit an entire hidden sector of particles, each with bizarre properties like dark photons that mediate forces between dark matter, or ultra-light fields that stretch across galaxies like invisible rubber sheets. The intergalactic medium, with its vast, quiet stretches, could be the perfect place to spot their effects. Imagine dropping dye into a river. You can't see the water's motion until the color spreads. Similarly, these particles might reveal themselves only by how they nudge the gas and plasma between galaxies over cosmic time. Every null result in underground labs and every unexplained blip in space telescope data tightens the noose around these phantoms or cracks the door open wider. The answer might come from an unexpected direction, a glitch in a particle collider, an anomaly in a neutrino detector, or even a strange twist in the afterglow of the Big Bang. One thing's certain, if these particles are out there hiding in the cosmic fog, they're not just footnotes in physics. They're keys to unlocking the universe's deepest secrets. And the intergalactic medium, vast and silent, might be the only witness willing to talk. Imagine a galaxy not as a static island of stars, but as a living, breathing entity, exhaling colossal streams of gas into the void, only to inhale some of it back in a cosmic dance of destruction and renewal. These are galactic fountains, and they're one of the most dynamic feedback systems in the universe. Picture supernova and stellar winds blasting gas hundreds of thousands of light years upward, where it cools, condenses, and rains back down to fuel new generations of stars. It's a self-regulating cycle, like a planetary water cycle, but on an unimaginable scale. Yet something's amiss. Observations reveal that a significant fraction of this gas never returns. It's as if the galaxy has sprung a leak, losing precious star-forming material to the intergalactic medium with no clear explanation. The mechanics of these fountains are both violent and elegant. When massive stars die in supernova explosions, their energy flings surrounding gas outward at ferocious speeds, sometimes over 1,000,000 miles per hour. This material arcs high above the galactic disk, forming a glowing halo of ionized plasma detectable by ultraviolet telescopes. Given enough time, the gas should radiate away its heat, grow denser, and plummet back down like a cosmic waterfall. In the Milky Way, astronomers have spotted these returning flows, cold clouds of hydrogen falling toward the disk at over 200,000 miles per hour, replenishing the raw materials for future stars. But here's the puzzle: while some gas cycles back, up to half of it seems to vanish permanently, lost to the vast intergalactic reservoir. One explanation lies in the delicate balance of forces governing these outflows. If the ejected gas reaches too high or moves too fast, the galaxy's gravity might not be strong enough to recapture it. Think of tossing a ball into the air, throw it gently and it falls back, hurl it hard enough and it escapes Earth's pull entirely. Galaxies with weaker gravity, like dwarfs, are especially prone to this bleed out. But even massive galaxies lose gas, suggesting other factors are at play. Magnetic fields might play an unexpected role, not just restraining the outflows, but occasionally flinging material beyond recovery like a slingshot. Or perhaps interactions with neighboring galaxies and the surrounding intergalactic medium strip away the fountain's falling rain before it can return. Then there's the wild card: heating from active galactic nuclei. Supermassive black holes at galactic centers can unleash torrents of energy, supercharging fountain gas to temperatures where it stays diffuse and buoyant, resisting recapture. Observations of galaxies like Messier 87 show vast bubbles of million-degree gas inflated by black hole jets, regions where fountain material might be heated beyond the point of no return. Simulations suggest this process could explain why elliptical galaxies, rich in black hole activity, often appear gas-poor compared to their spiral counterparts. But the real enigma is the gas that does escape. Where does it go? Some might linger in galactic halos for billions of years, a diffuse shroud awaiting some future trigger to collapse. Other fractions could merge with the intergalactic medium, contributing to the cosmic web's invisible scaffolding. The most intriguing possibility: this lost gas might seed entirely new structures, drifting until gravity pulls it into the next generation of galaxies far in the future. Every unanswered question about galactic air forces us to reconsider how galaxies evolve. If they're losing gas faster than predicted, it could mean earlier exhaustion of star formation, leading to red and dead galaxies far sooner than models suggest. Or perhaps this lost material is secretly fueling unseen processes like the growth of dark matter halos or the enrichment of the intergalactic medium with heavy elements. The answers might lie in next-generation telescopes like the James Webb and Athena, which can trace these flows with unprecedented clarity. Until then, galactic fountains remain a mesmerizing reminder. Even the mightiest structures in the universe are anything but self-contained. They breathe, they bleed, and they shape the cosmos in ways we're only beginning to fathom. What if the universe contains not just dark matter, but an entire shadow universe of matter particles that pass through everything we know like ghosts through walls? This is the radical premise of the shadow matter hypothesis, a theory suggesting there could be a parallel sector of particles interacting with ours only through gravity, remaining otherwise invisible. Picture two overlapping worlds, each unaware of the other's existence, yet subtly shaping the cosmos through their combined gravitational pull. The idea builds on an eerie observation when astronomers mapped dark matter using gravitational lensing. The way massive objects bend light from distant galaxies, they sometimes find structures that shouldn't exist. Certain filaments of the cosmic web appear too dense, their gravitational effects too pronounced for the amount of visible and dark matter we've accounted for. It's as though an unseen hand is adding extra weight to the scales, warping spacetime in ways current models can't explain. Shadow matter could be that invisible influence, a hidden layer of reality tugging at the universe from just beyond our perception. Testing this requires cosmic detective work. One approach examines the alignment of galaxies and dark matter halos. In our known universe, galaxies tend to spin along the filaments of the cosmic web, their orientations influenced by the gravitational tides of nearby structures. But if shadow matter exists, its additional gravitational pull could twist these alignments in unexpected ways, leaving faint statistical fingerprints in galaxy surveys. Teams analyzing data from the Sloan Digital Sky Survey have reported odd deviations in some regions, subtle twists in galactic orientations that don't fit standard simulations. Could these be the first hints of shadow matter's influence? Another clue might lie in the distribution of cosmic voids. These vast, empty regions are sculpted by gravity's push and pull, with their sizes and shapes revealing the forces at play. Some voids appear slightly smaller or more misshapen than simulations predict, as if an unseen mass is compressing their edges. Shadow matter, thinly spread but pervasive, could explain these anomalies. Unlike dark matter, which clumps around galaxies, shadow matter might distribute more uniformly, subtly altering the geometry of emptiness itself. The most tantalizing possibility involves collisions between shadow matter halos and our own. If these two sectors occasionally interact beyond gravity, through some feeble, undiscovered force, their encounters might leave behind bursts of rare particles or distortions in magnetic fields. Experiments like the Large Hadron Collider are probing these frontiers, searching for exotic particles that could act as bridges between the sectors. Meanwhile, radio telescopes scan the cosmic web for anomalous synchrotron radiation, which could betray shadow matter's presence where it tangles with interstellar plasma. Skeptics argue these anomalies could stem from incomplete dark matter models or unresolved astrophysical processes. But the shadow matter hypothesis offers something bolder, a universe far richer and stranger than we've dared to imagine. If proven, it wouldn't just add another ingredient to the cosmic recipe. It would reveal an entire parallel kitchen operating unseen beside our own. Every unexplained gravitational wiggle, every odd alignment in the cosmic web becomes a potential whisper from this hidden realm. And as our telescopes and detectors grow more sensitive, we might finally catch shadow matter stepping into the light. The universe is a violent place. Galaxies collide, stars explode, and black holes shred matter into swirling chaos. So why does some of the gas floating between galaxies defy this cosmic pandemonium? Vast swaths of the intergalactic medium remain eerily calm, their atoms drifting in serene silence despite the surrounding mayhem. It's like finding a perfectly still pond in the middle of a hurricane, and this cosmic tranquility has astronomers scrambling for explanations. One clue lies in the delicate balance between motion and resistance. When gas moves, it should create turbulence, eddies, and whirlpools that ripple outward for light years. Yet when scientists examine certain regions, particularly the thin filaments connecting galaxy clusters, they find plasma smoother than expected. The surprise stems from supercomputer simulations, which predict far more churning based on the gravitational tug of war between galaxies and dark matter. Something seems to be suppressing the chaos, acting like an invisible cosmic damper. Magnetic fields might hold the answer. Threading unseen through the intergalactic medium, these force lines could act like shock absorbers, preventing gas from spiraling into disorder. Picture dropping a handful of iron filings into water without magnets. They scatter randomly, but introduce a magnetic field, and they align into orderly patterns. Similarly, intergalactic magnetism might constrain plasma's motion. channeling its energy into structured flows rather than letting it dissolve into turbulence. Observations of galaxy clusters support this regions with strong magnetic fields often show strikingly uniform gas distributions, as though an unseen hand ironed out the wrinkles. But there's another twist. Some of this eerie smoothness might be an illusion of scale. What looks calm from a distance could be teeming with microscopic turbulence, tiny ripples too small for our telescopes to resolve. It's like gazing at the ocean from an airplane. The surface seems flat until you descend and see the waves. Advanced radio telescopes hunting for faint distortions in background quasar light might soon settle the debate, revealing whether the gas is truly serene or just hiding its chaos in the fine print. The implications stretch beyond mere curiosity. Turbulence isn't just cosmic scenery, it shapes how galaxies form and evolve. Chaotic gas resists collapsing into stars, while smooth flows might feed galaxies more efficiently. If magnetic fields are secretly enforcing order, it could rewrite how we model the cosmic web's evolution. Even more tantalizing is the possibility of unknown physics at play. Perhaps exotic particles or dark matter interactions subtly smoothing the gas in ways our theories haven't yet imagined. Every new observation peels back another layer, revealing an intergalactic medium far more nuanced than we once thought. And in that quiet between the explosions and collisions lies a mystery that could redefine our understanding of cosmic order. One of the most perplexing gaps in our cosmic map isn't a missing galaxy or a hidden void. It's an eerie absence of gas signatures in certain slices of the universe's timeline. Astronomers call it the redshift desert, a stretch of cosmic history where the intergalactic medium seems to vanish from our observations. It's as if someone took an eraser to the universe's ledger, wiping away crucial entries during critical epochs. The mystery isn't just about what's missing, it's about why these gaps appear precisely when the cosmos was undergoing its most dramatic transformations. Redshift, the stretching of light toward longer wavelengths as the universe expands, acts like a cosmic clock, telling us how far back in time we're looking. When we examine gas clouds at redshifts between 1.5 and 3, corresponding to a period roughly 2 to 4 billion years after the Big Bang, something strange happens. The expected absorption lines from hydrogen and other elements grow faint, sometimes disappearing altogether. This isn't a small discrepancy. It's like searching for water in a desert and finding only parched earth. The question is stark: was the gas truly absent during this era, or are we just not seeing it? One compelling explanation ties the redshift desert to the universe's most energetic adolescence. This period coincided with peak quasar activity, when supermassive black holes in galactic centers were devouring matter and blasting out torrents of radiation. These quasars didn't just shine, they sterilized their surroundings, ionizing nearby gas so thoroughly that it became nearly transparent to our telescopes. Picture a forest fire sweeping through a landscape, leaving behind only charred ground. The quasar's ultraviolet fury might have burned away the detectable signatures of hydrogen, creating artificial voids in our observations. But there's a twist. Some regions of the desert show more nuanced patches where gas appears to clump and thin in unexpected ways. This suggests another possibility: the gas wasn't destroyed but redistributed. During this epoch, galaxies were forming stars at breakneck speeds, pulling vast reservoirs of gas into their cores. The intergalactic medium might have been siphoned into these stellar factories, leaving behind stretches of unusually rarefied space. Imagine a bustling city during a gold rush. Resources flood toward the centers of activity, leaving the outskirts barren. Then there's the observational blind spot theory. Our tools have limits. The Lyman-alpha forest, the spectral fingerprints of hydrogen gas, becomes harder to trace at certain redshifts due to overlapping absorption lines from other elements. It's like trying to pick out a single voice in a choir when everyone's singing the same note. New instruments like the James Webb Space Telescope are now probing these eras with unprecedented precision, hunting for faint signals earlier telescopes missed. Early data hints that some missing gas might have been hiding in plain sight, its signals too diffuse or redshifted for older technology to catch. The stakes are high. If the desert reflects a real scarcity of gas, it could mean this era hosted a cosmic bottleneck, a time when galaxy formation slowed because fuel ran low. But if it's an illusion, our models of how matter cycles through the universe might need recalibrating. Every new observation walks the line between these two possibilities, teasing us with clues but refusing to surrender the full story. And somewhere in that elusive balance lies the key to understanding how the universe transitioned from its fiery youth to the structured cosmos we see today. Flashes of energy so intense they could outpower entire stars, lasting just microseconds, streak through the intergalactic medium like cosmic lightning bolts. These aren't the predictable bursts of quasars or supernova. They're rogue discharges flickering into existence and vanishing before our telescopes can even blink. Some release more energy in a fraction of a second than our Sun will emit in 100,000 years, yet leave no visible trace behind. The mystery isn't just their staggering power, it's what could possibly create such violent, fleeting sparks in the near-perfect vacuum of space. One leading theory plunges into the realm of dark matter. If certain particles of dark matter collide and annihilate, they could unleash concentrated bursts of gamma rays, like invisible fireworks detonating in the void. Picture two phantom stars made entirely of dark matter, orbiting each other unseen until their inevitable crash. The moment they touch, their annihilation could ignite a pulse of energy so bright it briefly outshines galaxies. The challenge: these particles would need properties beyond our current models, interacting just rarely enough to explain the sporadic nature of the flashes. Yet tantalizingly, some of these events align with regions where dark matter is predicted to clump, as if the universe is dropping breadcrumbs toward an answer. Then there's the primordial black hole hypothesis, the idea that the early universe birthed countless miniature black holes, some no heavier than a mountain. Over billions of years, these relics would slowly evaporate through Hawking radiation, their deaths culminating in explosive gamma-ray finales. It's like a cosmic version of static electricity, tiny, invisible accumulations of energy suddenly discharging in a spectacular spark. The timing fits. If these black holes were light enough, they'd be reaching the end of their lifespans now, peppering the cosmos with their dying flares. But the real enigma lies in the distribution of these events. Unlike fast radio bursts, which often trace back to galaxies, intergalactic lightning seems to strike in true emptiness, far from any known celestial structures. This raises even wilder possibilities. Could these be echoes of cosmic strings, theoretical defects in spacetime left over from the Big Bang, snapping and releasing pent-up energy like rubber bands stretched to breaking? Or evidence of extra dimensions where energy bleeds into our universe through unseen fissures? Every unexplained flash forces us to reconsider the limits of physics. New observatories like the Cherenkov Telescope Array are now scanning the skies for these ephemeral signals, hunting clues in their afterglow. What they find might rewrite our understanding of dark matter, black holes, or even the fabric of spacetime itself. Because in the darkness between galaxies, the universe keeps throwing switches, lighting up the void with questions we're only beginning to ask. Galaxies aren't supposed to move like this. Across the cosmos, thousands of galaxy clusters are caught in a silent current, drifting toward a single point beyond the edge of the observable universe as if pulled by an invisible hand. Astronomers call it dark flow, a mysterious, large-scale motion that defies the uniform expansion we expect from the Big Bang's aftermath. These aren't random wanderings. Meticulous measurements from the Planck satellite and X-ray telescopes reveal clusters streaming at speeds topping 2 million miles per hour, all aligned toward a distant, unexplained attractor. The implication is staggering. Something massive, something beyond our cosmic horizon, is tugging on the fabric of space-time itself. At first, skeptics dismissed it as a measurement error, perhaps scattered light from our own Milky Way mimicking motion. But the signal persisted. When researchers mapped the peculiar velocities of over 1,400 galaxy clusters using the kinematic Sunyaev-Zeldovich effect, a way to track motion by how it distorts the cosmic microwave background, the pattern held. Clusters billions of light-years apart moved in eerie concert, like leaves caught in the same unseen river, the odds of this alignment being coincidence. Less than 1 in a million, yet the culprit remains invisible, lurking somewhere in the unobservable darkness beyond the cosmic light horizon. This is where the theories ignite. One radical explanation suggests dark flow could be the gravitational echo of another universe. In multiverse scenarios, our cosmos might be one bubble among countless others in an eternally inflating space-time foam. If a neighboring bubble universe passed close enough to ours in the distant past, its gravity might still be warping our galaxy clusters, imprinting a preferred direction on the cosmos like a fingerprint. It's as if we're detecting the wake of a ship that sailed out of sight long ago, except the ship is an entire universe, but not everyone buys the multiverse ticket. Alternative explanations dig into the flaws in our own cosmic maps. Could the dark flow be an illusion caused by inhomogeneous inflation, an uneven stretching of space-time during the universe's first trillionth of a second? If certain regions expanded faster than others, they might have left behind density variations vast enough to pull clusters off course. Others propose supervoids, gigantic, underdense regions of space whose repulsive gravity, a quirk of dark energy's influence, might be nudging galaxies outward in a way that mimics flow. The most unsettling possibility, dark flow might be forcing us to rewrite cosmology's rulebook. Standard models assume the universe is isotropic, the same in all directions on the largest scales. But if this motion is real, it hints at a cosmos fundamentally lopsided, with structures and forces operating beyond our current physics. Future missions like the European Space Agency's LISA gravitational wave observatory could test these ideas by hunting for primordial ripples in spacetime that might carry clues about the universe's asymmetric infancy. Until then, dark flow remains a cosmic puzzle, one that might either unlock the multiverse or reveal just how much we still don't understand about our own. Black holes aren't the cosmic vacuums we once thought. They might actually leave behind ghostly hairs in their wake. According to Stephen Hawking's revolutionary theory, these gravitational monsters don't just swallow everything forever. They slowly leak energy in the form of quantum particles, a phenomenon we now call Hawking radiation. But here's the twist. As black holes evaporate, they could imprint faint, quantum-scale structures onto the fabric of spacetime itself, like phantom hairs clinging to the universe long after the black hole is gone. The wildest part, these hairs might not just be theoretical curiosities. They could subtly alter the energy balance of the intergalactic medium, leaving traces we're only beginning to hunt for. Imagine the universe's empty spaces as a vast ocean, and black holes as whirlpools dotting its surface. When a whirlpool vanishes, it doesn't just disappear, it leaves behind ripples, eddies, and maybe even debris. Hawking's hairs could act similarly, lingering as quantum perturbations in the surrounding gas and radiation fields. These wouldn't be literal strands, of course, but ultra-fine distortions in spacetime's geometry, each encoding information about the black hole's lost mass, spin, and charge. Under the right conditions, they might even interact with passing photons or cosmic rays, nudging the energy flow of the intergalactic medium in ways that defy classical physics. The real challenge is detecting such subtle fingerprints. Quantum gravity, the elusive theory bridging Einstein's relativity with quantum mechanics, predicts these hairs should exist, but their signals would be unimaginably faint. Think of trying to hear a whisper in a hurricane. Yet some researchers speculate that advanced gravitational wave detectors, like the proposed Laser Interferometer Space Antenna LISA, might one day catch these whispers. By analyzing the gravitational noise between merging black holes, scientists could hunt for anomalies, tiny deviations from expected waveforms that betray the presence of Hawking's phantom strands. Even more tantalizing is how these hairs might influence the intergalactic medium's thermal history. If they transfer even a fraction of their energy to surrounding gas, they could heat it in ways our models don't account for. Certain unexplained temperature fluctuations in cosmic voids or odd absorption lines in quasar spectra might trace back to this quantum graffiti. It's a long shot, but if proven, it would mean black holes don't just shape the cosmos through gravity, they etch their legacy into the very fabric of space long after they're gone. Of course, not all physicists are convinced. Critics argue that Hawking radiation itself is too weak to leave detectable traces, let alone these hypothetical hairs. Others suggest alternative quantum gravity models where information escapes black holes through entirely different mechanisms, leaving no hairs behind. The debate cuts to the heart of how we understand information, entropy, and the fate of matter in the universe. What's undeniable is the audacity of the idea that the darkest objects in existence might shed delicate quantum threads, weaving unseen patterns into the cosmos. And if we ever find them, it won't just solve a mystery about black holes. It'll reveal a hidden layer of reality where the universe's smallest and largest scales are intimately, bizarrely connected. The universe wasn't born quietly. It erupted into existence with a burst of expansion so violent it stretched space-time itself. This inflationary epoch, lasting less than a trillionth of a second, left behind cosmic scars, primordial gravitational waves rippling through the fabric of reality. Today, these waves could still linger in the intergalactic medium like echoes in a canyon faint, but carrying secrets about the universe's first moments. Detecting them isn't just about proving inflation happened, it's about uncovering how it happened. Different inflationary theories predict different wave patterns, some smooth and uniform, others twisted and knotted. These variations would imprint themselves onto the cosmic microwave background, the afterglow of the Big Bang, and subtly influence how matter clumped together in the early universe. The BICEP experiments at the South Pole have spent years scanning the sky for this signature, hunting for a telltale swirl pattern in the CMB's polarization that would betray gravitational waves' presence. But there's a twist. The intergalactic medium might hold another clue: actions. These hypothetical particles, if they exist, could have interacted with inflationary gravitational waves in ways that left unique fingerprints on the distribution of gas between galaxies. Picture dropping dye into a flowing river. The way it swirls reveals hidden currents. Similarly, actions might have caused primordial waves to twist the intergalactic medium structure in specific, detectable ways. The challenge: these signals are unimaginably faint. Gravitational waves from inflation would stretch across billions of light years, their wavelengths so vast they'd make entire galaxy clusters look like specks. Action-induced patterns would be even subtler, buried in the noise of cosmic expansion and later structure formation. Yet next-generation telescopes and precision CMB mappers are inching closer. Every improvement in sensitivity peels back another layer of cosmic static, bringing us nearer to hearing the whispers of inflation itself. What's at stake goes beyond mere confirmation. If we find these echoes, they could reveal whether inflation was driven by a single field or a cascade of them, whether our universe is one bubble in a frothing multiverse. They might even hint at physics beyond Einstein, where quantum gravity leaves its mark on the largest scales. The intergalactic medium, often seen as mere empty space, could be the parchment on which the universe's first story was written. And we're just learning how to read it. Rising from the heart of the Milky Way like twin cosmic geysers, the Fermi bubbles stretch 25,000 light-years above and below our galactic plane, a pair of gargantuan gamma-ray structures so immense they dwarf the entire visible disk of our galaxy. Yet these colossal formations aren't unique to us. Across the universe, other galaxies harbor similar enigmatic bubbles, their origins whispering tales of violence written in high-energy light. The real puzzle: some appear sculpted by the fury of supermassive black holes, while others bear the fingerprints of cataclysmic starbirth, forcing us to question whether these structures share a common genesis or if the universe has multiple recipes for building them. Take NGC 3079, a galaxy 300 million light-years away, where Chandra's X-ray vision revealed bubbles nearly twice the size of our own. Unlike the Milky Way's diffuse gamma-ray glow, these are bounded by sharp shock fronts as though carved by a scalpel. The culprit: a supermassive black hole's relativistic jets, pumping energy into the surrounding gas like a cosmic blowtorch. Simulations show these jets can inflate bubbles over millions of years, their boundaries acting like pistons that heat interstellar gas to millions of degrees. Yet when astronomers examined our own Fermi bubbles, the evidence grew murky. Their smoother edges and lack of clear jet signatures suggest a different architect, perhaps a long-ago starburst episode where thousands of supernovae collectively erupted, driving winds powerful enough to punch through the galaxy's disk. Then there's M87, home to the famous black hole imaged by the Event Horizon Telescope. Here, the bubbles aren't just large, they're dynamic, twisted into helix shapes by the black hole's spin. This tells us magnetic fields play a starring role, channeling and sculpting the outflows like invisible hands molding clay. The Milky Way's bubbles show their own magnetic oddities, polarized radio waves hinting at vast, organized field lines woven through their structure. Are these remnants of ancient jets we can no longer see, or proof that starburst winds can magnetize gas on galactic scales? The plot thickens when we study bubbles in quieter galaxies. UGC 3672, a modest spiral with no active black hole, sports X-ray cavities filled with ultra-hot gas. These seem tied to periods of frenzied star formation, where stellar winds collectively shoved material outward. Yet curiously, their energy content matches the Fermi bubbles almost exactly, as if nature has a preferred quota for such structures, regardless of their creator. This duality raises profound questions. Could black holes and starbursts be two sides of the same cosmic coin, capable of producing eerily similar structures through different means? Or are we missing a deeper connection, some universal feedback mechanism that regulates galaxies' growth? New clues emerge from the intergalactic medium itself. The outer fringes of these bubbles often mingle with vast reservoirs of million-degree gas, visible only in X-rays. Some show signs of frosting layers of heavy elements like oxygen and neon deposited by the bubble's expansion. These chemical tags act like forensic evidence, revealing whether the outflows came from star fusion byproducts or black hole accreted material. In the Milky Way's case, the elemental mix points squarely to stellar origins, yet other galaxies' bubbles tell different stories. The grandest mystery might be timing. Our Fermi bubbles are young by cosmic standards, perhaps just a few million years old, while others persist for hundreds of millions. Do they reinflate periodically, like lungs breathing in and out? Or is each galaxy allotted a handful of these eruptions across its lifetime? The answer could reshape our understanding of galactic life cycles, revealing how often galaxies wake from slumber to reshape their surroundings. One thing's certain: whether forged by black holes or stars, these bubbles are more than just celestial curiosities. They're the universe's way of venting its energy, an exhalation that shapes the fate of everything around it. Some corners of the universe don't just feel empty, they defy physics by being too empty. Astronomers call it the too thin gas problem. Vast regions where the intergalactic medium isn't merely sparse but improbably, almost unnervingly rarefied. These aren't just voids, they're cosmic deserts where gas densities plummet to levels that simulations struggle to explain. Imagine pouring water into a sieve and watching it vanish without a trace. No droplets, no mist, just inexplicable dryness. That's the puzzle we're facing on a galactic scale. Take the Boötes void, a sprawling emptiness spanning 300 million light-years. While most cosmic voids still contain wispy filaments of gas, this one pushes the limits. Measurements from ultraviolet telescopes show gas densities up to 10 times lower than predicted, as if something or someone siphoned it away. The oddity isn't just the lack of gas, it's that our models of structure formation can't easily recreate such extreme desolation. When cosmologists simulate the universe's evolution, even the emptiest regions retain faint webs of hydrogen. Yet observations reveal patches where the cosmic web seems clipped, its threads severed without a visible cause. One theory points to an elusive phase of matter. Could this missing gas exist in a form we can't yet detect? Under extreme conditions, hydrogen might transition into a bizarre quantum state, perhaps a Bose-Einstein condensate, where atoms lose their individuality and behave as a single wave. In this invisible cloak, the gas wouldn't absorb or emit light the way normal matter does, slipping through our observational nets entirely. Alternatively, the gas could be ionized to such high energies that its spectral signatures blur into the background noise of the cosmos, camouflaged by its own heat. Then there's the dark energy factor. As the universe accelerates outward, dark energy's repulsive force might be stretching voids to unprecedented thinness, like taffy pulled too far. Some simulations suggest this expansion could tear gas clouds apart at the seams, dispersing atoms so widely they become virtually undetectable. The catch: this process should leave subtle temperature variations in the cosmic microwave background, a signal we've yet to confirm. But the wildest possibility challenges our understanding of gravity itself. Modified Newtonian dynamics, or MUND, proposes that gravity behaves differently in extremely low-density environments. If true, gas in these voids might not be missing at all, just distributed in ways our current math doesn't capture. It's like searching for a shadow in a room where the light bends unpredictably. The object is there, but our tools can't trace its shape. What makes this mystery so critical is its ripple effect. Gas is the universe's raw material, the stuff of future stars and galaxies. If vast reservoirs are vanishing into undetectable states, or if voids grow emptier than physics allows, it could mean our cosmic inventory is wildly incomplete. Every unexplained vacancy forces us to rethink how structure emerges, how energy flows, and what secrets might hide in the darkest, quietest corners of space. And until we solve it, these ghostly voids will keep whispering the same unsettling question: where did everything go? The cosmos has a dirty secret, it's far too clean. Not in the pristine, untouched sense, but in how evenly heavy elements like iron, oxygen, and carbon are scattered across the intergalactic medium. This uniformity is baffling because the factories that produce these metals, supernova and merging neutron stars, are anything but orderly. They're cosmic grenades detonating in chaotic, localized bursts. So how does their debris spread so evenly across millions of light-years, like smoke from a fire perfectly dispersed through a stadium? The answer might rewrite our understanding of galactic ecology. Picture a single supernova explosion. In an instant, it flings metals outward at nearly 10% the speed of light, a shrapnel storm of newly forged elements. Left unchecked, this material should clump around its birthplace, creating chemical hotspots in the galaxy. Yet when astronomers measure the intergalactic medium, they find iron-to-hydrogen ratios suspiciously consistent, whether near a bustling galaxy cluster or in the deepest void. It's as if some unseen cosmic bartender has stirred the universe's cocktail to perfection. Galactic winds might hold the key. These aren't gentle breezes but million-degree plasma tsunamis, powered by the collective fury of thousands of supernova or the jets of supermassive black holes. Simulations show these winds can reach velocities over 2,000 kilometers per second, fast enough to escape a galaxy's gravity and inject metals directly into the intergalactic medium. But here's the catch: without a mechanism to mix everything smoothly, these outflows should create chemical gradients like dye dispersing unevenly in water. Yet we don't see that. The metals appear homogenized, demanding an additional layer of physics. Enter turbulence, the universe's ultimate blender. The intergalactic medium isn't a static pool. It's a dynamic fluid, churned by gravitational tides from passing galaxies and shock waves from ancient collisions. Magnetic fields add another twist, weaving through the gas like invisible whiskers that channel and stir heavy elements across cosmic distances. Over billions of years, this constant agitation could erase chemical fingerprints, smoothing out disparities until every region shares a similar metallicity. Think of it as cosmic diffusion on a grand scale, where time and motion erase the traces of individual explosions, but the plot thickens with delayed mixing. Some metals might hitch rides on cosmic rays, high-energy particles accelerated by supernovae, which can travel hundreds of thousands of light-years before depositing their cargo. Others could be locked in dust grains, flung far and wide by radiation pressure before finally dissolving into gas. These processes introduce lags, meaning the iron we detect today might have been forged in stars that died billions of years earlier, their remains only now completing a journey across intergalactic space. The most tantalizing clue comes from quasar absorption spectra. When light from these brilliant beacons passes through the intergalactic medium, it reveals not just the presence of metals but their ionization states. Some regions show highly ionized iron alongside neutral hydrogen, a mismatch suggesting external enrichment. It's like finding chili powder floating in a glass of milk. The ingredients shouldn't coexist unless something mixed them from afar. This could imply metals are delivered ready ionized, pre-processed by the very forces that expelled them from galaxies. Yet puzzles remain. Certain ultra-faint dwarf galaxies exhibit bizarrely high metal content despite minimal star formation, as if they absorbed someone else's pollution. Could galactic cannibalism, small galaxies merging and exchanging enriched gas, play a role? Or do we need to consider more exotic mechanisms like dark matter interactions that preferentially transport heavy elements? The answers lie in next-generation telescopes like the Extremely Large Telescope, which will trace metal distribution with unprecedented precision. Until then, this paradox endures, a universe that scrubs away its own fingerprints, hiding the violence of its past in perfect, puzzling harmony. There's something invisible flooding the cosmos, an excess of radiation that shouldn't exist. Not from stars, not from black holes, not from any known source. Astronomers call it dark radiation, and it's one of the most perplexing clues hidden in the intergalactic medium. Imagine turning on a Geiger counter in a supposedly empty room and hearing it click wildly, as if the walls themselves were radioactive. That's the enigma we're facing on a cosmic scale, an unexplained energy signature that hints at shadowy particles decaying in the void or perhaps even realms beyond our dimensions. This mystery first surfaced in precise measurements of the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light reveal how energy was distributed in the early universe, and the numbers don't quite add up. There's more radiation than standard models predict, as if an invisible hand cranked up the universe's thermostat. The discrepancy is subtle but persistent, like finding an extra guest at a party where everyone's already accounted for. One explanation, dark radiation, could be the fingerprint of exotic particles decaying dark matter, sterile neutrinos, or even relics from higher dimensions slowly leaking energy into the cosmos. The plot thickens when we compare this excess to known radiation sources. Ordinary neutrinos, those ghostly particles streaming from stars and supernova, leave a distinct mark on the cosmic microwave background. Their influence is well documented, like a familiar signature in the universe's ledger. But dark radiation behaves differently. It doesn't match the neutrino backdrop. It's as if someone swapped out a familiar instrument in an orchestra for one that plays notes we've never heard. Some theories suggest these rogue particles could be mirror neutrinos from a parallel sector of reality, or Kaluza-Klein modes vibrations echoing from curled-up extra dimensions predicted by string theory. Then there's the dark matter connection. If certain dark matter particles decay over astronomical timescales, they might produce dark radiation as a byproduct. Picture a slow-burning cosmic fuse, releasing energy so gradually we've only just noticed its cumulative effect. Simulations show this could explain oddities in galaxy cluster collisions, where missing energy hints at invisible particles carrying away momentum. The catch: if dark matter decays, it challenges the assumption that it's stable, a cornerstone of modern cosmology. Yet the evidence keeps mounting. Observations of distant quasars reveal anomalous absorption lines, as if their light passed through a fog of unknown particles on its journey to Earth. The most mind-bending possibility: dark radiation might be a gateway to extra dimensions. In some higher dimensional models, gravity leaks into adjacent realms, leaving traces in our universe as excess radiation. It's like living in a house with hidden rooms. You might not see them, but you'd feel the draft where walls should be solid. Experiments like the Large Hadron Collider are probing these ideas, hunting for particles that flicker in and out of our dimensional plane. Meanwhile, telescopes scour the intergalactic medium for subtle distortions in light that could betray hidden forces at work. What makes this mystery so tantalizing is its scale. Dark radiation isn't confined to galaxies or clusters. It pervades the entire cosmos, a whisper of physics beyond our current understanding. Every unsolved anomaly, from the universe's expansion rate to the distribution of galaxy clusters, might tie back to this invisible energy. And as detectors grow more sensitive, we're inching closer to answers. One day, we might look back and realize that dark radiation was the first clue to a reality far stranger than we ever imagined. For all the unsolved riddles lurking in the intergalactic medium, from phantom radiation to unexplained voids, one haunting pattern emerges. The deeper we look, the clearer it becomes that our cosmic inventory is incomplete. These aren't isolated puzzles, they're interlocking pieces of a grander mystery, hinting at physical laws beyond our textbooks. Take the coldest gas clouds defying thermodynamics, the shockingly uniform metal distribution, and the over-ionized voids. None should exist under standard models. Like detectives finding the same fingerprint at unrelated crime scenes, astronomers are tracing these anomalies back to a potential culprit. Gaps in our understanding of gravity, quantum fields, or even space-time itself. The missing link might be hiding in plain sight, gas that's not actually missing, just transformed. Picture a chameleon-like phase of matter, shifting between states we can and can't detect. Some theorists propose dark gas, not dark matter, but ordinary hydrogen and helium cloaked by quantum condensation or exotic magnetic binding. In this shadow state, it wouldn't absorb or emit light the usual way, slipping through observational nets. Others speculate about sterile baryons, particles that interact only through gravity, making them ghosts to our telescopes. The kicker: these ideas aren't pure speculation. Quasar absorption lines occasionally show faint, unidentifiable dips, whispers of something blocking light that doesn't match any known element. Then there's the dark matter entanglement. If dark matter interacts with normal gas even weakly through some unknown force, it could redistribute heat and particles in ways that explain both the too thin voids and the too rich oxygen pockets. Simulations introducing just a 1% interaction rate between dark and ordinary matter reproduce eerie matches to observed structures. It's like discovering wind patterns you never noticed because you didn't realize air could push against invisible sails. The real game changer. We're on the verge of unprecedented tools to test these radical ideas. The James Webb Space Telescope's infrared eyes are dissecting primordial gas clouds with precision, hunting for chemical anomalies that could betray new physics. Meanwhile, the Square Kilometre Array, a global radio telescope network launching this decade, will map the cosmic web's hydrogen in 3D, exposing hidden flows and clumps. Its sensitivity is so extreme it could detect gas densities previously considered theoretical, like finding a single rain cloud in a desert. But the most thrilling possibilities lie beyond instrumentation. If these telescopes confirm anomalies that defy tweaks to existing models, we might witness the birth of a new physics paradigm, one where the intergalactic medium isn't just the space between galaxies, but the canvas on which the universe's deepest secrets are painted. Every paradox, every unexplained signal is a thread tugging at the fabric of our understanding, and when one thread finally unravels, the whole tapestry might follow. From the ghostly threads of dark matter weaving through the void to the unexplained lightning of rogue gamma-ray flashes, these 30 mysteries paint a portrait of a universe far stranger than we ever imagined. Each one tears at the fabric of our cosmic textbooks, missing matter that defies accounting, galaxies without stars, oxygen deserts where there should be none. The intergalactic medium isn't just empty space. It's a frontier of unanswered questions where the laws of physics seem to rewrite themselves in the darkness between the stars. Consider the paradoxes we've uncovered. Gas colder than logic allows, bubbles of radiation with no visible source, entire galaxies drifting toward some unseen attractor beyond the edge of the observable universe. These aren't isolated oddities, they're threads of a grander tapestry, hinting at forces and particles we've yet to name. The cosmic web, the dark flow, the whispers of sterile neutrinos, all of them point to a reality more intricate than our best telescopes can grasp. But here's the thrilling part. Every mystery is an invitation to rethink, to explore, to peer deeper into the abyss and ask what else might be hiding in plain sight. Maybe the answer lies in quantum vibrations echoing from extra dimensions, or in the slow decay of dark matter particles older than time itself. Or perhaps the truth is something so unexpected it hasn't even crossed our theorists' chalkboards yet. That's the beauty of the cosmos. It doesn't yield its secrets easily, and that's why we keep searching. Because somewhere between the galaxies, in the quiet and the chaos, the universe is still writing its story. So tell us which of these mysteries grips your imagination the most: the phantom pull of dark flow, the enigma of Hawking's quantum hairs. Drop your favorite in the comments, and don't forget to subscribe for more journeys into the unknown. After all, the greatest secrets aren't just in the stars, they're in the spaces between.